Welcome back to Advent of Code 2017, day 22. Last time we had a problem involving, what was it? Oh, this. It ended up being an alright problem, to be honest. It was just a bit fiddly to code. Alright, 22. So, what have we got? Diagnostics indicate that the local grid computing cluster has been contaminated with the Sporifica virus. The grid computing cluster is a seemingly infinite two-dimensional grid of compute nodes. Each node is either clean or infected by the virus. Okay. To prevent overloading the nodes, which would render them useless to the virus, or detection by system administrators, exactly one virus carrier moves through the network, infecting or cleaning nodes as it moves. The virus carrier is always located on a single node in the network and keeps track of the direction it is facing. To avoid detection, the virus carrier works in bursts. In each burst, it wakes up, does some work, and goes back to sleep. The following steps are all executed in order one time each burst. If the current node is infected, it turns to the right, otherwise it turns to the left. It infects the current node, okay. The virus carrier moves forward one node in the direction it is facing. Fine. That's straightforward. Diagnostics have also provided a map of the node infection status. Clean nodes are shown as dot. Okay, infection is shown as hash. Virus carrier begins in the middle of the map facing up. For example, suppose you were given a map like this. And the middle of the infinite grid looks like this. Okay, fine. Yeah, I get it. This doesn't look hard at all, but part 1 at least. After 10,000 bursts, how many bursts cause a node to become infected? Okay. That is our map, alright. Where do we start? We start in the middle of that. Whatever. Okay, we'll find the length of it. Okay. Okay then. This looks easy, this part. We just have to simulate 10,000 steps of moving forward and turning. My chair's a bit. Okay. Alright, so let's begin. So we want to, okay, we'll read the input. So we'll say, it's 25 by 25, right? Yeah. Okay, so let's just create a grid which is, let's say int. So everything starts at 0, which means clean. So we open the input for each line. Let's say for I line in enumerate. For J in enumerate dot strip. Okay. If car is hash, then grid of ij equals 1. Otherwise it's just defaulted to 0. We don't need to do anything else. Let's just check this works. Print grid. Yeah. Okay. So we're not storing the zeros. That's more efficient, really. But okay. So let's say start equal n equals length of. Let's just n equals m equals length of line, no, not line. M equals length of line minus 1. Okay, that's the width. We want the height. I mean, I know it's square, but let's just write it in a way that you can give this any rectangular input. So the length, because that's just the more sensible way to code it. So n would be character in whatever, n equals I plus 1, that'll give us m and n, right? Just make sure we got the right. It should be 25, 25. (25, 24), and m equals length line minus 1. Just do dot strip. Sometimes the final line doesn't have. I get it. Okay, final line doesn't have the. What? Line dot strip. should be 25, not 24. Why? M equals length. Oh, yeah, I shouldn't have the -1 then. Okay. That makes sense. Okay, got it. Alright. Good, good, good. Right, so start equals n to m over 2. So we're in the dead center, right? Yeah. Okay. Direction equals, what was it? In's in the middle of the map facing up. Up is basically going to be -1, going row, decreasing the row, 0. The column will not change. Hello, 16-bit. You're learning Python. Nice. Yes, I am a big fan of Python. In fact, I don't really use anything else these days. It was my first proper language that I learned. Technically, I started with C. I hated it. Some of this makes sense now. Yeah, it's a very readable language, even to someone who doesn't know Python. But once you know, I mean, some of the weird things in Python are the list, the way you access indices and slices. Once you know those things, then the notation makes more sense a lot of the time. So, yeah, this problem is involving a virus, which is, it's a pretty simple problem description actually. We have a grid, which looks like this. We're in the center. It's an infinite grid, but we only see this is just what it looks like in a small slice. The virus sits here, and every turn if the current node it's sitting on is clean, which is a dot, then it turns right. No, it turns left. Otherwise it turns right. And then it infects the current node it's sitting on, or cleans it if it was already infected. So a hash becomes a dot becomes a hash. And then it moves forward one, and then repeats that process. So it moves forward, basically inverts the current node, and then turns either left or right, depending on what that node was. It's basic simulation. Doesn't seem to be difficult. There's no algorithm needed here. So what about? So this is the starting grid. We are starting in the dead center. So I think this is correct. Divide width and height by 2. Did you know Python was... What is... Oh, named after Monty Python. Yeah, I did know, yeah. Yeah, it's pretty funny. And yeah, the official Python documentation has lots of references to Monty Python. Like using lots of variables, like, I don't know, like references to the Dead Parrot sketch and stuff. It's pretty funny. And like using spam and eggs for variable names and things like that. Okay, so we're sitting in the middle, facing up, which is -1, 0. And now we just repeat this 10,000 times. So for underscore in range 10,000. So now we just have to do the exact steps. So it says first, if current node is infected, turn to the right. Okay. If grid, let's not call this start, call it current. Grid current direction equals, all right, how do you turn to the right? So right is 0, 1, down is 1, 0. Is it this? Is it minus your whatever your previous direction was, but the second parameter, and then minus whatever the first parameter was? I forget my linear algebra. So does that work? So if it was starting at minus 1, 0, we now go to 0, 1. That works for that. And then if we do that again, it'll be no. Then we'll be brought back to up. 0, 1. We want to now go to 1, 0. I'm gonna take that minus sign off. It's like that. Okay, does this work? So, okay, I gotta write this out. So, I'm up. So if I take direction 1 minus direction 0, I end up at 0, 1. That's right. Now if I do this again, I end up with 1, 0. That's down. And then finally, it will be 0, minus 1, left. And then from left, yeah, that works. Else, it's the other way around. So you do minus, plus. That's turn left. So change the facing, now what? If the current node is clean, okay, we invert whatever the current node is. So we say grid current equals 1 minus grid current. All right, and then finally we move forward. So current equals current 0 plus direction 0, current 1 plus direction 1. That's it. And then what are we recording here? We want to count how many times we turn a 0 to a 1. Okay. So we want to say if grid current was not infected, it's going to become infected. So we record 1, add 1 to the count. And then finally just print count. Five, 1, 8, 2. Correct. That was an easy part 1, I think. Well, compared to the problem I did yesterday. Part 2. Oops. As you go to remove the virus from the infected nodes, it evolves to resist your attempt. Well, they're evolving now. Now, before it infects a clean node, it will weaken it to disable your defenses. If it encounters an infected node, it will instead flag the node to be cleaned in the future. So there's basically 4 states that you can rotate through. Clean becomes weakened, weakened becomes infected, infected becomes flagged, and flagged becomes clean. Okay. Alright, so if you're clean, you go left. If you're weakened, you don't turn at all. If you're infected, you turn right. If you're flagged, you turn 180. Okay. Just easy modification. And then we follow this rotation. Super interesting to me that I'm trying to follow along. So what kind of tutorial were you following? Were you using the Python website tutorial or like some other guides online? This is a pretty good website to try and practice some of the stuff you've learned. Although I wouldn't recommend going past. Well, I mean, you can try, but I wouldn't recommend going too far into the days because they do actually require some mathematical stuff as well that is beyond what the starting tutorials would teach. But using this mobile app is kind of like Duolingo. Oh, okay. Oh, we have to do this 10 million times. Actually, that's not actually that bad because we're just doing a single step each time. So that's fine. If it were in the billions, maybe we'd be in trouble. But... Okay, so. Okay, so guess I need to just, well, I can't really I have to scrap everything I've stored here and use it for part 2, start fresh for part 2. So let's say we do this again. Alright, so we clear the grid. We fetch the starting set again. Alright, so I guess we want 0 if it's clean, 1 if it's, what's it? weakened, 2 if it's infected, 3 if it's flagged. Okay. Let's make a note here. We want 0 clean because everything's clean by default. 1 weakened. 2 infected. 3 flagged. Okay, so again, this all counts as infected. So this is actually going to be 2 instead of 1. Is that how it works? Yeah. Okay, so the starting state is correct now. We got this is 0s and 2s. No, just 2s because the 0s are... We don't need to worry about them because everything's 0 by default. Got the grid. Let's just try printing it. Yeah, we got... Current is same as before. Direction is same as before. Why doesn't it like this? No new... Okay. Now... Basically want to do this again. But this time it's 10 million. Alright, so... What are the steps? If... it is clean, it turns left. If infected, it turns right. Okay, so if grid current is 2, turn right. Else if grid current equals 0, turn left. And if grid current equals, and the other one is if it's flagged, we reverse direction. If it's weakened, we do nothing, so we don't need to do anything there. So if it's flagged, we reverse. So if it's 3, direction equals minus first parameter minus second parameter. And then we turn, well, turn 180. Okay, so this is the turning phase. And now the status phase. And then we've got the movement phase. Right, so the status phase, or let's call it infection phase. How does the infection phase work? Clean becomes weakened, so 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 0. So that's easy. We just say grid current equals grid current plus 1. Modulo 4. So that'll bring it back, that'll wrap around back to 0 after 3. If, well, what are we counting? If grid current is 1, count, because that means it's going to become infected, which is 2. Then we add the direction, and then just print the count. Alright, let's try that. It's running now. It's doing 10 million, but it shouldn't take long. There we go. 2.5 million. That sounds perfect, because if it's 10 million, and you're running around changing these states between 4 different states, then on average, about a quarter of them will end up infected, because they'll keep all of the states will keep rotating. So that sounds right. Roughly a quarter of 10 million. Almost exactly. Because there's 4 different states, so. Correct. That was a nice, easy problem. As long as, I think, people are going to run into problems. If I've seen people try to create, you know, 2-dimensional arrays of size 10 million or something for these types of problems. This is where the beauty of Python dictionaries comes into place, because you don't. I think people make the mistake of creating a huge array of zeros. But you don't care about the zeros, because everything's 0 by its default. You only care about the things which are not 0. So you don't need to store 10 million zeros, you just need to store 2.5 million non-zeros, essentially. Alright, okay, let's get ChatGPT on the case. I think ChatGPT will have no issue with this, it seems straightforward enough. Okay. Let's see. Is he using a default dict? Not quite, but... but he is sort of checking by default whether there's it. Okay, I prefer my way because default dicts are nice. In fact, I've used default dict several times in like company interview questions, and the interviewers always liked that because they didn't know about the default dict. But it's so much cleaner than having to write this if so and so not in grid, or that. Instead, you can just write that right there. Let's try it then. Five two 9. Was that what I had? No, it wasn't. It was not. It's not far off, but it is kind of far off. It's about 100 off, which is... It's not 1 off, so something's definitely a bit wrong here. See if we can actually debug it. I'm not... that's what I did that. Wait, what do you mean? Why is he doing %4? What? Oh, that's the direction. Okay, that's correct. Actually, that's a smarter way of doing it than what I did. Whatever. But what has he done wrong? Num infections is +1. I don't know. I don't know why it's wrong. Alright, I'll just tell him it's wrong then. I made an error in the code. The direction indices were not matching the given problem's description correctly. I like how you just tell him he's wrong, and within milliseconds he realizes what his error was without you giving any hint. So that's the key. Whether or not you even tested it, you could just say you're wrong, and then you'll get a more correct answer. Okay, fine, whatever, let's try it. Five, 2, 4, 9. No, that's still wrong. Same answer. Nothing's changed. Misunderstanding in the interpretation of the problem. His code looks fine. See, I don't know why he's getting the wrong number. It's strange that it's only about 100 off, because... wonder if it's parsing. He's parsing it wrong. Split lines. I've never even used... What is split lines? I'm gonna look this up. Python split lines. Splits a string into a list where each line is a list item. Oh. Okay, fine. It's just shorthand for dot split, where the new line character is the parameter to split on. Alright, let's... I'll try and use it in the future, but... 5249 is still wrong. Okay, I'm calling that a fail then. I've tried 3 times. It's really weird though. I am really curious as to what he did wrong. Is current direction equals 0? Actually, yeah, that's correct. 0, what? 0 minus 1. Wait, he's using the first parameter to be the row or the column? I'm not that interested. Let's move on. So that's a win for me. '23. We're almost on Christmas Day. Okay, day 23. Coprocessor conflagration. You decide to head directly to the CPU and fix the printer from there. As you get close, you find an experimental coprocessor doing so much work that the local programs are afraid it will halt and catch fire. Halt and catch fire. Halt and Catch Fire is an American television series as well. What? What's it about? Oh, it is about computers, okay. Machine code instruction that causes the CPU to restart the computer. I never heard anyone use the phrase halt and catch fire. Maybe it's just an old thing. This would cause serious issues for the rest of the computer, so you head in and see what you can do. The code it's running seems to be a variant of the kind you saw recently on that tablet. What are they referring to here? Yeah, okay, I remember the assembly problem. The general functionality seems very similar, but some of the instructions are different. Set XY. Set register X to the value of Y. Sub XY. Decreases register X by the value of Y. Mul XY. Multiply. J and Z. Jumps with an offset of value of Y, but only if X is not 0. Okay. That's the same as before, pretty much. The coprocessor is currently set to some kind of debug mode, which allows for testing but prevents it from doing any meaningful work. If you run the program, your puzzle input, how many times is the mul instruction invoked? Okay, it's basically just use our old code, but with even fewer instructions, because we're not using the weird stuff that we had before, so... like the sound and the recall. Alright. Let's bring up 18 again to remind ourselves of how that worked. Alright, so yeah, we probably want default dict. Register equals default dict, okay. Instruction set is a list, register is a default dict with open input. Line and read lines in start append line.strip.split. Is that correct? Strip.split sub d. Yep. Okay. What else did we do in 18? That was a nice method. Copy that in. That saves us having to do lots of if else. Right. PC equals 0. Okay, so we copied this whole lot, but we actually have to, we can discard some of these instructions. So that one we don't need. Okay, so we got set. What did we keep? Set, sub, mul, J and Z. Set. Well, there's no sub. Okay, we can change add to sub. Mul. So these two we get rid of. JNZ jump value Y if X is not 0. So that needs to be not equal to 0. And that's an N, but otherwise it's basically the same. Okay. And what are they asking us? How many times is the mul instruction invoked? Okay, so we got count equals 0. Count plus equal 1. Part1 print count. Is that it? Run. 6241. Correct. Just literally just copy in the code from 18. I didn't even have to discard the irrelevant code because it wasn't being invoked anyway. Alright, part 2. Now it's time to fix the problem. The debug mode switch is wired directly to register A. You flip the switch, which makes register A now start at 1 when the program is executed. Immediately, the coprocessor begins to overheat. Whoever wrote this program obviously didn't choose a very efficient implementation. You'll need to optimize the program if it has any hope of completing both while Santa needs that printer working. Oh man, this is one of these problems where you have to actually figure out where to make shortcuts. It's quite difficult to do. You can't just write code to solve your problem. You have to actually optimize the assembly code. The coprocessor's ultimate goal is to determine the final value left in register H once the program completes. This is one of those problems that's actually almost impossible for ChatGPT to solve, really, but we'll see. After setting register A to 1, if the program were run to completion, what value would be left in register H? Alright, so let's just test it. It's gonna get stuck in an infinite loop. That's what they're implying. Let's just try it anyway. Alright, so reset the register. Put A to 1. PC to 0. And then we just do this again, basically. And then we print register H. That, in theory, is the answer. It'll just take too long to do that. Let's try it. And yes, as they stated, my computer's fan is starting to speed up a bit, so let's stop that now. Okay, so what the heck do we do? Oh, I hate these ones because you have to really look at what's going on here. Alright, let's try and follow this by eye, see what actually sort of happens overall. We set B to be 81, set C to be B. Okay, B and C are both 81. Jump, if not 0, A by 2. So A starts at 1. Okay, so we jump by 2. So we go to this line here. Multiply B by 100. Okay, so 8,100. Subtract 100,000. And set C to be B as well. Okay, so B and C are now both some big negative number. And C also subtracts a further 17,000. Fine. F is 1, D is 2, E is 2, G is D, E, G is also 2. Multiply G by E. G subtract B. Oh my god. So if we didn't do this jump here, what would happen? We would get to this line here. Jump. So this is a jump. There's no condition here. It's jump if 1 is not equal to 0, and it's not. So we always jump 5. So we go 1, 2, 3, 4, 5. So we skip this weird thing here. So if how far back do we ever jump? Jump not set G2. So this jumps forward. This jumps back 8. It's 1, 2, 3, 4, 5, 6, 7, 8. Okay. This one jumps back 13. This jumps forward. This jumps back 23. So that's like... to here. Okay. So it seems like this all keeps happening. When does this end? This ends when we execute this line here, which tells us jump 3, i.e. end of program. So that happens when G is 0. So when G is 0, the program ends. And what does that mean? It means, well, G is B. We subtract C. So when B and C are equal, the program ends. Oh god. This is evil, this kind of problem. So we need to identify new instructions we can introduce, which kind of eliminate blocks that we're doing too many times. So like, how on earth do I do that? Set G sub T minus 1. Let's just read through this again. F set to 1, D set to 2, E set to 2. G is set to 2. Multiply G by E. It's like 4. G subtract B. So B is some really big negative number. Alright, so line 28 is where the program might terminate. It will terminate... No. 20, this one here. 30, which is actually 29. Index 29. So... No. Sorry, no, this one. This is the one which matters. 28. If G is 0, we will exit the program. So we need to look at what's happening to G and see why it's not 0, or how long it would take for it to get to 0. When do we ever touch H? Only time we ever touch H is here, where we subtract 1. So we're counting how many times. So if PC, yeah, if PC is 28, print register G. PC equals 28. Are we never hitting that line? Let's see what lines are we hitting. Print PC. It's just stuck between 14 and 19. So this one and this one. Sorry, this one. So we keep doing this until G is 0. Okay, so B and C so that's F, D, E, G, D, G, E, G, B, B. B and C are never altered, except B is altered later on, but they're never altered in that. Okay. So C is never changed, ever. B is altered. We do minus 17. So C is a fixed constant. Don't understand. So E subtract 1. Let's try printing out what the register looks like. I want to know. Okay, let's have a look at this. A is 1, B is that number, C is that number, F is 0, D is 2, E is that, G is that. 6136, 6138, 6140, 6142. G is increasing by 2. Whenever it's at 14, it's increasing by 2. Whenever it's at 19, so we want to know when it will get past 19, because after it gets past 19, ZG minus 8. Alright, let's see. What is it doing in this loop? So it goes back 8, so it goes here. Set G to be D. Alright, multiply G by E. Okay. Subtract B from G. Fine. So if G is 0, we do this line here, set F to 0. That seems to be important, because this G is sort of never 0. But G is decreasing, so eventually that will happen. Huh. So the only time h will ever be altered, ever, will be when f is 0 here. For f to be 0 here, we have to have this line executed. And for this line to be executed, we need g to be 0. For g to be 0 here, let me think this through. So we can reverse engineer what h is going to end up as. So yeah, that's reasonable. Okay, so f is 0. For f to be 0, we need a g to be 0. For g to be 0, then this means g has to be equal to b here. That means so g equals b before this line. That means g times e equals b before this line. That means d times e equals b before this line. That means d times 2 equals b. That means 2 times 2 equals b. That means b equals 4 before this line. So if b is 4, that will guarantee h will be minus, that will make h minus 1 through that chain of events. So the question is, when will b ever be 4? Well, when is b ever changed? Here. But when that never gets hit, say, but the interesting thing here is there's only one opportunity for b to be 4. B starts at this number, and then we keep subtracting 17. So there is one occasion where b is 4. Can't work this out. What the heck am I supposed to do here? So B starts at 108, 108, 100. If we ever hit this line here, we subtract 17 and then just jump all the way back and do all this stuff again. So 32, jump to here and do all this again. So we might as well, and that resets F, D, E, G, C and B are fixed. So we might as well just skip ahead and set B here. Alter the input. Set B to be 4, because that's the only time anything interesting happens. And then all these all get reset, so it's not like we care. We need to, I don't know, try running that. Hang on, we have to stop part 1 because part 1 is interfering now, so. Part 2, so. We don't need to count. So once B is 4, then interesting stuff starts happening, it seems. Just stop, stop, stop. Okay. What is happening now? Is that reasoning correct? So when B is 4, so whatever happens here doesn't really matter because it's just changing. Oh, but what about sub B minus 17? So we're adding 17. What? Oh, no, hang on, this is wrong then. Have another look at this. So B is 108, 100, okay. The only time B ever gets modified is, I mean, here, but then that happens once only. Here, B subtract minus 17, so B adds 17. Ah, so B can never be 4. B can never go down, it can only go up. So we subtract, so we add 17, and then we go back 23, so we end up here, and then we do all this again with the new value of B. So when will anything interesting happen? So as I said before, H will be decreased if f is 0. If f is 0, here, and we'll only get to this line if g is 0. We'll only get to this line if g equals b. Okay. Which translates to meaning d equals b, because we've set g to be d. So d equals b. D. So d equals b minus 1. I can't. I don't know. I hate these problems. It's gotta be the easier way to do this. What's actually going on with these numbers? So b is not changing. Yeah, we need f to be 0. What are they getting at? Maybe we really just need to fully backtrack here from the end and not worry about what's happening in the middle. So, what is happening at the end again? So, when we exit the program, that means that has been executed. Okay, if that has been executed, that means g was 0. I need to make notes here. Alright, so for the program to finish, that means g is 0. Okay, g equals 0. That means here, g equals c before this. Set g to be b. So actually b was equal to c. Alright. So basically counting, and h was subtracted. So whatever, so h is basically counting the number of times b is equal to c. And f is equal to 0. So we're counting how many times f is equal to 0. That's not quite that. If b is ever equal to c, the program terminates. So that will only happen once. Now b keeps adding 17. Alright, starting to see what's happening here. So we've got b starts at 108, 100. C is always 125, 100. So here we keep adding 17 until b equals c, and that's when the program finishes. So every step in between, we're trying to work out whether or not how many values of b f will be 0 for. So let's backtrack now. So if f is 0, need a better pen. Okay, f is 0. So this block here just keeps repeating until g is 0. So we got so this keeps repeating until g is 0. Let's see if we can separate this block, to turn this block into something. So let's see. We set g to be d, multiply g by e, subtract b. Set f to be 0. So if g is 0 here, then f is 0. Interesting. So what this block is saying, it's saying d times e, take away b, if that's 0, then f is 0. If it's ever the case that d times e minus b, in other words, b equals de, Otherwise, we decrease E by 1. Set G to be E. Subtract B. This is ridiculous. What does this whole block translate to? This block. It's saying if B equals DE, then set F to 0. Okay, that's what all those lines at the start are doing. And then we subtract 1 from E. And if E minus B, so if E equals B, we break out of the loop. So there's basically 3 conditions. If B equals D times E, F is 0. And if E equals B, we break out of the loop. So it's basically a while loop. While E is not equal to B, so if there's any value for E for which what is D? So if D is ever equal to B, what's this saying? We decrease D. If D equals B, we carry on. Maybe I should just translate this into normal code, because this assembly code is... oh man. Yeah, maybe that's the way. Translate it into non-ridiculous code, so that I can actually read it. Yeah, okay, let's do that. So let's write this out as stop using the instructions. Translate this into so got a equals 1. Right, that's the starting condition. B equals 81. B equals 81. C equals B. Fine. C equals, let's just say C equals 81. Jump, not 0, A, 2. Okay. So we skip that one. Okay. B multiplied by 100. Alright. So just do that. B subtract minus 100,000. Okay, so B will be 100, 10, yeah, it'll be that number, which is what we're seeing. Set C to be B. Alright, well C is going to be that. C adds 17,000. Okay, so we get that number. That's fine. Okay. C never changes. B will change. Okay. So we have to identify all the jumps and what they do. So let's start with so this one is going to jump back to okay. This one is going to jump back to 12. This one jumps back to minus 23, so that's 9. Jumps back to 9. Okay, fine. So this is a while true loop. So f equals 1. Well, no. We need to identify where these are jumping. So this is jumping to 12. Okay. This one is jumping to 11. All right, so 11. So D equals 2. Okay, so f equals 1. D equals 2. And now from 11, line 11, we've got a while loop. Okay, so we're done this while loop here. While G is not 0, in other words, while D is not equal to B, while D is not equal to B, E equals 2. Now we've got another inner jumping. We've got this one, which jumps to 12. Okay. While E is not equal to B. And now for this inner loop, we've got set G to D, multiply G by E, so take away B, okay, I get it. So this block here is saying if DE equals B, if D times E equals B, if D times E is B, F equals 0. Either way, we move on to this bit now. E minus 1, okay. E minus equal 1. Sorry, E plus 1. That's important. Now, so that loop keeps going until E is equal to B. Then we break out of that loop. We get D plus equal 1. And then we break out of that loop. Okay, this is looking good now. Alright, so now we're out of this loop. We're on to the next bit. If F is 0, right, so remember H is 0 to begin with. If F is 0, H minus equal 1. Okay. Okay, now we take B, we subtract C, B take away C, so if B equals C basically, we break out. Interesting. Break out of that loop. And then what? B minus equals 17. Okay. B. And that's it. That is the code right there. All right, now I can actually look at it and see what's happening. Okay, that's crazy. If B C break B minus equals 17. So in other words, this while loop is actually while B is not equal to um, 1, 2, 5, 1, 17. 17 more than C, because when it's that, hang on. Let's put some numbers in here. Change the order of these. Let's say B minus equals 17 here. Instead, and say if we are, because this is the same as saying if we are what am I trying to say here? We're at 1, 2, 5, 100, we break, okay. Alright, so that's the same as saying if we're at this, 083, and did the subtraction beforehand, then we break. And that lets us do this, while B is not equal to that, do all of this. Okay, so that's simplified. C doesn't matter anymore, we're just using its value. A is 1. A doesn't actually matter in this whole thing. So that is the program. F is 1. So it's counting how many values of B have God, that's still confusing, but it's better now. Also, we're not minusing 17, are we? We're adding 17. So it's actually the other way around. We're saying that. Okay, now try printing some stuff. I don't know. Well, let's just try running this. Okay, it's infinite loop as we'd expect. Now, some of these while loops can be changed to ranges. So, for example, this is the same as saying for E in range 2 up to B. Yeah. That's nice. Alright, and then this one, D equals 2 while D is not okay. This one is the same as saying for D in range 2 up to B. Ah. So it's asking whether B, how many times... Oh my god, look how simple that is now. So if there's any number, any two numbers in the range 2 to B minus 1, such that B is those... Is it just counting if B is prime or not? So we have a B value. We're trying to work out if there are any two numbers, non-trivial numbers, that multiply together to give B. In other words, if B is non-prime. And if it's non-prime, then we subtract 1 from H. I get it now. Now, what could we do here? We can break out of this, because we don't need to try all the other values. See if that actually speeds up. We can break out of this whole thing, actually. Hang on. Sorry, don't need that. Alright, so now we are breaking as soon as we find a factor. Good. The other thing we can simplify is instead of going to B, we can go up to the square root, because we know there's no factors greater than the square root, so so it's going to be math dot square root B int plus 1, I don't know, something like that. So that cuts down the range quite a bit. And we don't need E. What we need is this is just a single loop. We say if B percent D is 0, F is 0, break. We don't need to find what its other factor is. That's a massive improvement. Done. Print H. Minus 909. Oh, please, 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 please. Alright, come on. No, it's wrong. I'm getting there. Am I? Oh! No, it's positive. H. Yeah, minus is a weird number, isn't it? Well, it's adding 1. Where is it? Because I keep getting confused with this sub. It's actually adding 1. Yeah, H plus 1. Damn it. Why did I never stop to think about that? Why am I subtracting 1 from 0? Okay, yeah, it's going to be that. Yeah, 909. It's 909. I don't think they're going to let me submit for a minute. Okay, 10 seconds left. Gotta be 909. So this whole program translates to finding how many values of B are prime, but non-prime. Oh my god. Right, good luck, ChatGPT. ChatGPT's not going to solve it, surely. No way is ChatGPT going to solve this. I'll have to paste the full assembly code to ChatGPT. That was actually a good problem. I was really annoyed at that at first. Then I stopped and translated it to, you know, readable code, not horrible assembly, and then it became clear what was actually going on. That is a skill that's not often tested in these problems, actually. So, yeah, that was a pretty well designed problem. I know he's going to fail on part 2, but we have to try part 1 anyway. To give him the chance to fail, at least. Oh, you... No way. That's okay. That is the most impressive thing I've seen ChatGPT do. He's immediately worked out that this is a prime finding program. From that, really? So he's come up with an is prime method and. Let's check it works. Okay, that is actually one of the most impressive things I've seen ChatGPT do. This is where it shines. Like, the amount of time I spent trying to translate that program into meaning, which is a very hard thing to do, but also a very human thing to do. It's a you're trying to assign a semantic meaning to a program rather than just know what it's doing syntactically. If ChatGPT could do that, then that's actually one of the main things we want AI to do for us. Well, he's not defined age. Let's tell him. Yeah, just set age equals 0. Okay. 910 times is what he says. 910. No. It was supposed to be 6,241. Huh. Okay, he's wrong. Okay. Oh, he's trying to count the number of non-prime numbers. Oh my... Wait, 909... He solved part 2. I never asked him to. That's actually unfortunate, because that means he's kind of invoking prior knowledge about this problem that he knows. I guess that makes it slightly less impressive that he realized it was about primes, but it's still, I assume at some point in the past he did actually work that out, because... So it's... Okay. Alright. 9... No. Invoked 910 times. What? He's still doing the thing with the prime numbers. Oh no. Wait, did I change? No, I didn't change it. I didn't modify this, did I? No, he's still wrong. Count. Alright, we'll see. Six, 2, 4, 1. Yeah. Alright, now we'll give him part 2. He already solved part 2, but I need him to solve it when I give it to him. He probably will, but... Yeah. Check the prime numbers between B and C. Well, yeah, not quite prime numbers between P and C, but prime numbers in steps of 17. Okay. I mean, he's done the efficient way of prime checking. That seems fine. So final value 909. Yeah, he solved it. Okay. Damn. That's impressive. How long did that take me? Long time. I almost lost hope there. I was just looking at that assembly code, just thinking how the heck am I supposed to assign any meaning to this? It's just a bunch of jumps and increments. Okay then. So that's a win for ChatGPT. A huge win for ChatGPT. That is the single best performance I've seen by ChatGPT on a problem. He did a very human thing there. Alright, fine. Should I keep going? If I do 24 now, then I... do I want to? Nah. Save it for tomorrow, because then we'll have 24 and 25 to solve tomorrow. That'd be nice. Yeah, so tomorrow will be Christmas Eve. And Christmas Day. And then I'll be done with Advent of Code 2017, and then in the future we can move on to 2018, because I still have 18, 19, and 21 to do before the actual Christmas comes this year. Hopefully. And I think in the future I'll stop invoking ChatGPT. It was an interesting experiment, but I get the point now. It's very smart. It can solve problems better than me. Yeah, I get the message. So I'll just stick to solving them myself. Alright. That's it. We'll be on tomorrow with the final two problems. So, see you next time.